Hi everyone, thank you very much for joining. I'm Julien Carron. I'm very happy to present this work, Are There Any Holes in the CMB Likelihoods? On behalf of my collaborators, Giulio Fabian, Anthony Lewis, Margareta Lembo. So what is this all about? I'll be talking about an effect related to CMB lensing. So CMB lensing are these 2 arc-minute size deflections of CMB photons as they travel through the universe. So this, of course, impacts in a very relevant manner the CMB spectra, and it must be taken into account for inference on conceptual parameters from the CMB. So in this work, the question we wanted to ask is the following. So in CMB data, there are a number of extragalactic sources. Thinking about point sources in radio or infrared, thinking about galaxy clusters. And these sources are correlated to the large-scale structures. And since this is what lenses the CMB as well, there will be a correlation between lensing effect and these sources. Now, some of these sources will be masked prior analysis for various reasons, at least some of them. So the analysis mask can correlate to the lensing effect in the CMB. So that eventually we may be looking at a CMB which is slightly different than from the full sky average. So the question is, does this bias at all the CMB spectra, and how relevant is that now and in the future? So the main motivation between this study was simply the need that there is now for a very precise and accurate understanding of data. We know that there are tensions, in particular, regarding measurements of the Hubble rate from supernovae, Risedal, and CMB, or similar data, as confirmed recently by the ACT release of this year. In Planck data, there was this peculiarity of that the residual of the TT spectra were preferring a larger lensing effect, as shown on the right figure here. So this, since our work is geared toward a lensing-like related effect, this drove our efforts for a while. And finally, the bottom plot here shows a comparison of the Planck mask and the ACT latest release point source mask on the same area, just to illustrate how much more sources there are with deep experiments. The number density of point sources becomes much higher, and this will still increase with future experiments like Simon's Observatory or CMBS4. So as I said, we may be looking at a slightly different CMB after masking, and what's happening can be understood as follows. So if we look at a CMB, an unlensed patch will appear magnified if it is in front of a kappa peak, so in front of a big lens. We'll see a zoomed in version of the CMB. If we see it through a trough, on the contrary, it would be demagnified. All distances are pushed towards smaller distances. So if the peaks are preferentially masked, we'll be left with a version of the CMB which appears demagnified. So this means that it will impact the CMB correlation function on almost all scales, and will reduce it on almost all scales. So we do expect some effect. We can understand this effect better in harmonic space by looking at the effect of a large fixed lens on the CMB. So this is usually called the squeeze limit. Just by considering one fixed lens and averaging, statistically speaking, over CMB modes to get the local form of the power spectrum on that patch of the sky. And there is a term doing this which is linear in lensing, which shifts locally all scales towards smaller scales, as I was saying for kappa trough. And this is actually what's been used in lensing reconstruction. So trying to reconstruct a lensing map from CMB data. So normally over the full sky, this would vanish because the kappa mean is 0. However, here we are preferentially masking high peaks, hence this will be negative, and this will enter the observed spectrum on your unmasked area. The second term is the usual peak smoothing of the CMB in the squeeze limit, which is second order in lensing. So there will be a bias on CMB spectra. Effects are expected on all scales. It's linear in lensing. There's more small scale power, simply because looking at the signs of the two contributions. In the same way, there will be less large scale power, and we do expect to see oscillations in this signature. I should say that this squeeze limit completely neglects the effect of small scale lenses, and there are a bunch of them. And for this reason, this is only a crude quantitative estimate. However, all the qualitative features I'm listing here are still quite correct. So to derive some analytical result for this bias, what we did was to set up some model of masks, just saying our mask is a function of the local value of some foreground field F, which is correlated to kappa. So F could be kappa itself in some extreme case, or related, I don't know, to the thermal Sunyaev-Silovich effect emission as detected in the CMB, or the Poisson distributed point sources, etc. Then we perform the calculation perturbative in the correlation between F and the lensing field kappa. Turned out this calculation produced very accurate results for all CMB spectra. So to get the term linear in lensing, you can see that it's enough to expand the lens temperature in unlensed time plus deflection times gradient of the temperature. So this is the lensing signal here, and this is the mask temperature. So the change in the 2-point correlation function is directly given by the correlation of these two terms. These two terms are shown here schematically on this figure, either seen through a kappa trough on the left or a kappa peak on the right, for a CMB hotspot on the top or a CMB cold spot on the bottom. So a CMB hotspot has a negative kappa trough lensing correction, and vice versa for a cold spot. But the sign of the correlation between T and delta T changes if you're on a peak, such that if you're really looking at the full sky, this naturally gives 0. Since we are masking more of these points, we do expect some negative correlation on average over the unmasked area. You can see that on kappa peaks, this masking here, the mask temperature and the lensing signal, they have the same signs. So there is some positive correlations between T and delta T, and this will not be undone by any mask deconvolution, which does not consider correlations of the mask to the lensing. So we, on small scales, we indeed expect a positive spectrum as a correction. So by contracting these terms, one obtains that the correction to the CMB correlation function is given by the derivative of the original CMB correlation function times some quantity, which is a simple interpretation of the mean change of distance between 2 points separated by R across the unmasked area. So W here, if I didn't say it before, is 1 across the unmasked area and 0 if there's a mask. So this might still appear quite complicated, but this function of R can be obtained in closed form for some simple model of mask like thresholds mask, so where we just say if the foreground field is higher than some value, there's a mask, otherwise there isn't. In this case, it's possible to derive an exact expression involving error function, etc. But anyways, there's a fairly general result for masks that are related to foregrounds which can be treated as Gaussian. It's built out of two terms. This one here, the product of the derivative of the correlation function times the correlation function of the foreground and the deflection. So this term here mostly sets the shape of the bias of our most relevant scales. So this function peaks at 10 arc-minute, which is the relevant scale in this problem. This acts as a very efficient, in Fourier space, this is a convolution, and acts as a very efficient transfer of power from large CMB modes to smaller scales. There will be a very large transfer of power to small scales, which is a bit like usual lensing, but even more efficient. The prefactor here is mostly setting the amplitude. It's a very smooth function. It's basically the mean value of the foreground field provided provided the mask is 1 at the point of the foreground and at a distance r. So basically this sets the amplitude as being, for example, very sensitive to the sky fraction that is masked. So here I'm showing some analytical prediction for the shape of this bias. So on the top panel, this is showing the difference in DL. So DL is LL plus 1 CL basically in mu k squared, in micro k squared. And you can see the qualitative features I've been talking about already. So we see some oscillations set by the derivative of the CMB spectrum. We see less large scale power, higher power on smaller scales. Here I'm showing two different curves, which corresponds to two different resolutions of the CMB experiment, one corresponding to Planck and one corresponding to SO. And in fact, the color should be switched. Obviously, Planck is the experiment with a resolution of about 4 arc-minute, not SO, and vice versa. The bottom plot shows the fractional change, so the relative deviation. And of course, what's striking on this figure is how large it can become at small scales. So this is 30% change, even if only 3% of the sky was masked in the very first place. So this is really the very, very efficient transfer of power from large to small scales. So in these curves, there's a fall off. That's because we are probing a smooth version of the kappa field. So I'm showing here as well the polarization spectra. So EE works a bit like TT. However, BB, the shape of the BB bias will depend a lot on your specific choice of estimator. So here we are showing naive deconvolution of simple pseudo polar spectra. So if you were to use a pure method which separates neatly the E and B modes, the bias would be much reduced, because here it's mostly due to the larger E mode entering the B estimate. So I've presented these exact results. These are only available for subspecific mask constructions. However, we want to stress that we can estimate the bias as well for basically any mask construction from simulations. So this requires a lensing map and the mask only. So the reason is that in real space, what's relevant, so the derivative of the unlensed CMB is known. What's relevant then is this mean change of distance. And this you can see that it has the form of a correlation function of a cross spectrum in real space of the deflection of the mask deflections times the mask and of the mask correlation function itself. So by going into Fourier space and calculating spectra, it's possible to obtain a prediction for this quantity. So here, by mapping the mask power spectrum onto real space, and the numerator by calculating the cross spectrum of the spin 1 mask deflection to the mask itself. Okay, then it's simple to feed this into your analytical prediction, and you get what you want. So here on this slide, I'm showing tests we perform on web sky simulations, which are a set of simulations, n-body simulations, carrying with it a number of lensing relevant effects. And what these figures show is basically that we do understand very well the shape and amplitude of this bias for a number of cases. So here I'm showing a mask built on the kappa field itself and mask built on the CIB map. And in both cases, we do a very nice fit. We see very strong effects in the fractional change in the spectra. Of course, this is very dependent on the sky area that is masked. So an important question is, do these biases enter current data or not? So our simulations at first suggested that Planck point source mask of 2% of the sky could indeed move around cosmological parameters by about 1 sigma, provided the mask traces kappa very well. However, we cannot expect the mask to trace kappa very well. A point source mask probably is more like a Poisson process, where we are not tracing all peaks well, but only a fraction of them. So we did perform empirical tests to try to see this bias in data. For instance, using as in the recipe before, but using the CIB and lensing maps as a tracer of the deflection, we can then cross that to the Planck mask and use this to build prediction. Or another possibility is to just change the mask that is applied on the data and look for differences in the spectra measured on these different masks. So none of this method gave a positive result, and the variations at the level of a few micro k squared were always consistent with expected cosmic variance. I wanted to say here that we can see this very specific bias signature on data, but only by using a mask that's specifically designed to show stronger effects. So for instance, this figure here is showing this bias signature. And what I've done is to build a F-sky 5% mask, directly thresholding the CIB map, which we know is very correlated to the lensing. So I've used the Janel map in that case. So I've added that mask and reconstructed the spectrum from the SMICA foreground clean map, and then I've compared differences to the official Planck Blick mask. And you can see both at the expected amplitude and shape this bias. So we've been looking as well at ACT data from the latest release. So here what I'm showing is their point source mask here. And what I've did was to take the ACT public lensing map as lensing tracer. Again, do this trick of cross-correlating with the mask, try to predict how large the bias would be. But all we can see are just variations that are consistent, or at least with the same amplitude than the expected change from cosmic variance. So we must conclude that at present, there is no such bias in CMB data. So finally, I'm showing here preliminary forecasts for Simon's observatory, which will still be quite a bit quite a bit deeper than the current data, and CMBS4. So Simon's in the top panel so plotted are the signal to noise on the possible detection of this bias. First, for the case of a point source mask, trying to emulate the way sources are detected and masked in current analysis, and extrapolating that to Simon's observatory. And you can see that if IL are included, the detection of this bias could reach several sigma. So it starts to be interesting, and one must certainly pay attention to that effect. So the TSZ signal traces in a much better way the lensing signal. So in TSZ, one could expect a much stronger bias. And even that's the case even for very small sky fraction that are masked. So here 0.6% of the sky is masked. But you can see that the detection signal to noise can reach 10th of sigma, 10 sigmas if the analysis goes to high multiples. And similar conclusion applies for CMBS4, where again, of course, it depends on the maximum multiple included in the analysis. So here are our conclusions. So we've been discussing a new possible bias on CMB analysis. This bias is due to possible correlations between the analysis mask and large-scale structure. So this introduces a signature in the spectra which is linear in lensing, and that would vanish on the full sky. So this bias can be very large and lead to parameter biases, provided the mask traces the lensing convergence very well. So you expect a bunch of effects that I've discussed, more small scale power shifts, etc. However, current realistic analysis masks are more tracing point sources, which traces in a much differently the lensing convergence, and this bias appears then to be negligible for current data. However, it might become soon sizable for next generation experiments, Simon's observatory CMBS4. And wanted to say here as well, this bias can be estimated from simulations for any mask construction or tested empirically on data as well. Finally, there will be also biases on the lensing construction. I've not mentioned that, but this is the topic of a paper in preparation by Margarita. So thank you very much, and looking forward to the discussion session and questions.